Hi, good morning, everyone. Welcome to the Pandora and Composer session. It's not a music session, sadly, but you will probably learn how Composer helps Pandora to manage the music data. I'm Feng. I'm a software engineer in Google Cloud. Also joining me today are Daniel from Pandora and Wilson, too, from the Cloud Composer team. So we'll start the talk by giving folks an overview of what is Cloud Composer, what kind of problem we're trying to solve, and what are some of the features in Cloud Composer. And then we're followed by Daniel on stage talking about the Pandora's experience of migrating their workflow orchestration to Google Cloud. And we'll wrap up the talk by some of the newer and the latest features that were just recently released. So we live in an increasingly complex world. In the context of data analytics, this means your data probably live in many different places, and every once in a while there will be new data processing framework that get announced. And maybe once you're done with your data processing, there might be different places you need to sort of upload your data processing results. Eventually you realize that it's very unlikely that you can finish all your data processing needs in a single system. It's very common that you have to stitch data processing jobs in different systems together and essentially put them in the form of a workflow. And once you have a workflow, and then ultimately comes the need of you want to be able to schedule that workflow, you want to monitor that workflow. Really, think about the only way, a way to help you to reduce complexity is through automation. And here, it's really important that you have a tool that could offload and manage all this complexity of scheduling and monitoring workflows on your behalf. With that purpose in mind, we design and develop Composer. It's built on top of the popular open source Apache Airflow, and that helps you to create workflows at ease, make it powerful for you to manage your workflows. So exactly how does Composer helps you to sort of reduce your workflow management complexities and help you to improve your workflow development? We focus on a few areas. Namely, the first one is really about, we want to make sure Composer being the orchestration choice when it comes to GCP. So what that means is we want to make sure that, from Cloud Composer, you could orchestrate and manage pretty much all your GCP-related workloads. Let it be ML jobs, data flow, data proc jobs. Second thing, as I mentioned earlier, we realized that the need that, today your data is likely going to live in different places, on-prem and on cloud. So we designed Composer on day one with that requirement that whatever orchestration solution we're going to introduce, that needs to work well in a hybrid cloud environment. Also, be able to come out with higher abstractions and also make it really easy for you to write your workflow. Especially think about if your workflow has tens or hundreds or thousands of tasks. Again, we want to make it really easy for you to be able to express workflows consist of that many of tasks. Finally, to increase reusability, because you have done all your development on Prime. We don't want to be the case that when you move to Google Cloud and you realize, now I need to redevelop all my workflows. So we really put open source in the core of Cloud Composer, and we make sure that whatever workflows you write, you develop, those can run in GCP. And then likewise, when you move certain workflows to on-prem, you find out you don't have to modify anything. Things should just work out of the box. So with those requirements in mind, and then we added a lot of more we started design development of Cloud Composer. And then one of the questions we often got was, how does Cloud Composer differentiate with a self-managed Apache Airflow? I understand that probably many of you have on-prem Airflow deployments, and you're wondering, what are some of the value-added pieces if I move to Cloud Composer? There are quite some of those. I'm going to probably highlight a few important ones. The first one is really about, a lot of those are really sort of centered around simplicity and also trying to help you to minimize your operational complexities. So we have like really convenient tooling, Cloud Console, API, and gCloud for you to manage your Cloud Airflow, Cloud Composer environment, and make it easy for you to, upload your workflow and inspect workflow status. Second thing, probably like 70 to 80% of people rely on the Airflow Web UI, and also, frankly speaking, that's also one of the distinct factors that draw people to Apache Airflow. So we understand the need. That's why we put a lot of thoughts on to make things easier for you to host your Apache Airflow web server and also make it extremely secure through our cloud identity aware proxy. And then when it comes to, Airflow has different versions. Some people choose to, there's also like different Python versions, since Airflow is developed in Python. So again, in Cloud Composer, we really help you to streamline and simplify the management of Python and Airflow versions, so that in Composer you can specify and then which Python Airflow version you want to use, and it also open the path for you to sort of like, upgrade from one Airflow to a different Airflow version. Given that, often the case that when you write your workflow, you realize that you may have external library dependencies. You may have customized operators. So that's why we also make it extremely simple for you to install and manage additional PyPy dependencies. Debugging and monitoring are common needs these days. Whenever you have workflow failures, so Composer comes out of the box with Stackdriver logging and the monitoring integration. So whenever you have issues regarding to a particular task, you would be able to find all the logs in Stackdriver. And finally, there are IAMs for you to sort of streamline your Composer environment management and manage permissions, who has access to what. We launched Cloud Composer last year during Google Next. It has probably been about 9 months. And since then, we added a lot more GCP operators. That's really why I want to highlight here. As you can see from the slide, pretty much we support all the bulk of GCP operators. You have Machine Cloud AI, Translate, Cloud Vision, Kubernetes. On the data side, you have Cloud SQL, Bigtable, GCS, and Spanner. So those are all really trying to make it easier for you to write workflows. So you don't really have to worry about how should I interact with these new systems. I also want to, as I mentioned, that writing workflows are easy, and Airflow has a very expressive mechanism for you to express your workflow. So in the next couple of slides, I just want to show you a quick overview of how a DAG or a workflow is developed in Composer or Airflow. So a little bit context of a history of Apache Airflow. It's a project that was originally developed by Airbnb and subsequently got donated to Apache Software Foundation. And since then, it has gained a lot of popularity in the community. It's a very, very active community. It has like a few hundred sort of contributors. Workflows are essentially expressed as directly a cyclic graph. That's why you probably have, for people coming from the Airflow community, you probably have heard them talking a lot about DAGs. DAGs really are essentially just workflows. This is an example DAG of how, kind of like a Hello World-ish workflow. It has about 3 tasks, and then you run different commands, and then you have ways to sort of like specify the dependency among your task. At the beginning, you do your standard import, like standard Python imports. Those really just to tell Airflow, hey, I want to, like the DAG and the DAG is the workflow, top level workflow construct. And after that, you just import whatever operators you think are useful in this case, we use bash operator, but there are Python operator, and then there's a lot of like GCP operators, such as say run BigQuery query operator. So many different operators are there. Once you're done with the import, then you put all your orchestration or scheduling arguments there, like things like who are the owner of this workflow, how often do you want to run, when do you want to start a workflow, when do you want to end the workflow, so on and so forth. And once you have the argument set up, then writing the workflow itself is actually really straightforward. With a top-level DAG definition, then you can specify your task, any task that you plan to contain in that workflow. As I mentioned, in this example, we use bash operator, but you can, in fact, use any operator. The nice thing really about Airflow is it has the flexibility for you to introduce your own operator. This is really, tying back to my early point about managing complexity. Be able to come out with higher level abstractions and be able to hide that complexity from your internal users is really one way for us to navigate this complex sort of workspace. Once you put everything together, you submit it to Cloud Composer. From that point onwards, Composer will take care of scheduling, running, and monitoring your workflows. This is a sort of like a typical web UI for you to access your workflow. From there, you would be able to inspect that, the graphic structure of your workflow, and also you would be able to inspect different logs, when it comes to individual tasks. They also have like a rich set of dashboarding for you to inspect, if you put all your task runs or like workflow runs together, how does the processing time fluctuates across different time runs? Sometimes that helps you to detect an anomaly in your workflow. Behind the scene, this is what happens. Cloud Composer creates a collection of GCP resources, and then leveraging those resources, those resources are collectively known as Cloud Composer environment. And then within that environment, we host Airflow scheduler, worker, web server, the database, and then the workflow storage. The same workflow storage is also used for you to store workflow artifacts. And then once you have your DAGs there, then you will be able to orchestrate and connect to a whole set of external systems. Earlier, I showed you really a simple example, but then really a DAG can be as complicated as this. Although the graph itself looks complicated, but actually the code behind the graph isn't that hard. So I just want to say that this is a real DAG we use within the Cloud Composer team to sort of dynamically generate Airflow Docker images. That's so far about a quick overview of Composer and Airflow. Next, I'll hand over to Daniel to talk about Pandora's move to Cloud Composer.
Good morning. My name is Daniel Barrett. I'm a staff engineer at Pandora. I'm here to talk today about our move to GCP with Cloud Composer from on-prem Airflow. Just to give a little history on scheduling at Pandora. Originally, when I started, we had a system of legacy Java schedulers. They were based in Java. They used the Quartz framework as the actual scheduler. They were completely developed in-house. So because they're developed in-house, it was very hard for engineers or analysts outside of analytics to create jobs in the framework. There wasn't a whole lot of online support either. It was all based off of whatever we documented internally. It had a limited UI that we developed ourselves. If we wanted to add new features, we had to go out and develop them ourselves. That also took place, when you're doing other work and other tasks. So a lot of times it was very slow to be developed in the UI. About 2 years ago, we started our migration to Airflow. The Airflow UI is full of features and incredibly easy to use. It has support, as Feng showed you, for various technologies within Google Cloud, and then also regular technologies that allow you to integrate with Hive and Hadoop and things like that we use to do our analytics processing. It has a very large online support community. If you run into any problems, it's very easy to be able to Google it and look it up, and somebody else has probably run into that same problem, and will allow you to be able to figure out a solution to your problem. It is all written in Python, and it is incredibly easy to develop new operators and sensors that will do custom tasks for you, things that you do over and over and over again. You can put those into operators and allow other developers to use them much more simply and not have to reinvent the wheel every time. Because it was open source and there was a large community behind it, it was very easy to onboard new engineers that had experience using Airflow. There was not a lot of ramp-up time. In our previous one, there was quite a bit of ramp-up time in a period where people were getting used to the legacy Java scheduler. That didn't have to happen in Airflow. There was another issue that we came across, and a lot of our analysts at Pandora would use cron to be able to schedule their Hive scripts in the past. This obviously is not a great solution, and it was very easy for us to be able to integrate the analysts to create Airflow tasks and jobs that could depend on other jobs and things of that nature. That made it much more simpler and robust than just running a cron script using Hive. We were also able to use a sensor to depend on other analytics jobs completion outside of your actual Airflow instance on-prem. After those 2 years, now we have approximately about 90 instances between development and production in Pandora. Airflow has been adopted very widely and very quickly. So there are 5 problems that we looked at that we had to solve when we moved from Airflow to Composer. One of them was during the migration, Composer and Airflow are both running in cloud and on-prem, and the issues between running them in 2 locations. There was also the question of how do we depend on a job finishing in either location? And then Composer is a true distributed framework. On-prem, we made the decision to deploy Composer to a single VM, so that it was a lot simpler for the deployment, so that we did not have to manage a distributed deployment of Airflow on-prem. And then how do we support analysts in creating jobs that run on Dataproc? Back on-prem, they were used to having a Hadoop cluster that was always on that they could submit jobs to anytime. Now they had to figure out how to actually run stuff on Dataproc itself. And then finally, how do we deploy code to Composer from an on-prem Bitbucket or a repository on-prem? So the first one that we solved was the job dependency solution. So for that, we have a Postgres database on-prem. Eventually, we'll move that to the cloud. And there is a metaservice REST API container that sits in front of that Postgres database that handles requests for jobs or tables that are finished, or code that is asking, is something finished for the day. So that allows jobs or tables to be set as complete for a specific day parameter. It would also allow you to get the status of a job or table for a very specific day. And so around that, we created an Airflow sensor that would ask the metaservice if a dependency is fulfilled. If you are depending on job X, you would create that sensor in your workflow, and it would say, is job X done for April 1st of 2019. And then on the flip side, we also created an operator that at the end of the Airflow workflow, you could set your dependency as complete, your table, your job, whatever it is that you were running. So this is what that looks like, from the architecture. In here, we have 2 Composer instances that are running in GCP and 2 Airflow on-prem. There is the metaservice with the Postgres database backing it. So for this instance, we would have a job populating a table running on Composer instance number 1. That job, there are several jobs that are waiting on that table to be done on Composer instance number 2 and on-prem 3 and 4. After the table is populated in Composer 1, it would send a status done to that metaservice in that Postgres API. That Postgres database. And then the metaservice would then tell 2, 3, and 4 that job is now complete, and then their workflows would be able to move on from there. There are a couple of approach drawbacks to this in GCP. One is that because our Postgres instance is on-prem, and because we have on-prem instances, it is required that we need a VPC network for our Composer instances in GCP. So currently, due to our networking model that we decided in GCP, we use shared VPCs, and currently you can only have one shared VPC network per Composer instance. So in a specific project, that means that we can only have one Composer instance that uses that job dependency framework. And also, if you have a table that needs historical, and for some reason it happened before we set up this framework, and that job, those tables or those jobs are not done in that framework, then we need some kind of dependency override to be able to process history where the dependencies are not set in the past. So the next problem we do is dealing with Celery. So Celery is the asynchronous task queue job scheduler used as the workers in Composer, and it has some drawbacks. So specifically, I had a job that was a scientist job that had 3 pipelines that were highly parallelized that we were going to move to GCP last year. So I took these pipelines, and I knew that it had 3 distinct parts, and I ran them manually on specific machines to determine what type of machine could handle each individual task. From that, I determined the actual machine type that I was going to use to handle these pipelines. So originally, what I did is I set up Composer with 3 worker nodes with the very specific machine type that I knew I wanted to be able to handle this task. It was an N1 standard 16 cores. When it came to actually scheduling those tasks, the Celery scheduler caused those nodes to be overwhelmed, because what it would do is it would actually schedule 2 tasks on one node and 1 task on another node, and then nothing on the 3rd node. It was not an even scheduling of tasks itself. And because my node type couldn't handle more than one of the pipelines, it would cause it to freeze. So this is what it looked like when it would actually execute. You would have the scheduler, it would execute one of them on worker 1, 2 of them on worker 2, and nothing running on worker 3. So the solution that I'd used to get around this is I created 3 VM instances of the type of machine that I wanted to, and I named them processor 1, 2, and 3. And then I shut those machine instances down. I then set up Composer with 3 normal nodes and 1 standard 4. And then I set up the Composer DAG to use those processor machines. And what I would do is my task would SCP fresh code from Composer over to the processor machines themselves. And then it would use an SSH command to run the pipeline on each individual instance. So this enabled the actual processing to happen on the processing machines and not on the Composer nodes itself. So what would happen there is my scheduler would schedule on worker 1 and 2 on worker 2, but then those workers would actually execute the code on the actual processor machines themselves. So I ended up with 1 task running on 1, 1 task running on 2, and 1 task running on 3. This enabled the process to happen the way that I actually wanted it to happen. At the end of the processing, when everything was done, I would then shut down processor 1, 2, and 3, so we were no longer getting charged for those to use those nodes. This is what the resulting DAG looked like. If you look at the very beginning, you'll see a start VM instances task. This is where I would start up processor 1, 2, and 3, and then I would wait for those instances to fully start up. I then had tasks to SCP the code over to each one of those VM instances. And then I would run the scripts. And then I would have a couple of different tasks that would do some other processing and some local data cleanup on each one of those VM instances. And then at the very end, you see at the very last one, I would stop all 3 of those VM instances because we don't need them running until they're ready to go the next day. So the next problem we had to look at was, how do we make Dataproc easier for analysts to use? Analysts are, like I said before, they're used to having a Hadoop cluster that is always on and accepts their jobs at any time. They may have to wait for resources, but they could just fire off queries and fire off tasks and send them to this Hadoop cluster. Dataproc is a little bit different than that. Dataproc, you have to know a little bit to be able to create a Dataproc instance. You have to understand it a little bit more. What are worker nodes? Some of the properties that are needed to start up a Dataproc instance. So like I said, it was a bar to entry for analysts to use the Dataproc to run their schedule queries. So what we ended up developing was a batch job framework. And this was developed with a Google contractor called Nudesic. This was a batch job framework that requires minimal coding and really not hardly any Dataproc knowledge whatsoever. It would require them to create config files that just defined their SQL, the SQL tasks that they had, and the variables that were going to be put into those SQL tasks. And then the DAG was dynamically configured from those config files themselves. The config files would define external and inter-DAG dependencies, sensors based off of other jobs that were running on other Airflow instances on-prem, the piece that I showed you earlier. You would define those in the config files for your SQL. And you would also define inside of the DAG what SQL files depended on other ones so that they could then be set up correctly in a DAG. It would also provide a way to instantiate a Dataproc cluster for each SQL statement run using only the number of workers needed. And to do this, there was a heavy use of Dataproc workflow templates. The Dataproc workflow templates would start up a cluster for the batch job. They would run the SQL file on that cluster, and then they would delete that cluster afterwards. We found that this was the best way to use Dataproc. It was repeatable and was less prone to error than some of the other ways that we looked at running Dataproc and running SQL files on Dataproc. This is all the code that was required to be able to create this dynamic DAG. So this create batch DAG operator was what actually went through all of the config files and constructed the DAG itself. This code can be copied from one project to the next one. So the analysts would not really need to know any Python whatsoever in order to run their batch jobs. This could be Hive, this could be Spark, and several other different ways of running stuff. From that code came this DAG right here. So this DAG was created using that code, using config files that were set up for it. Like I said, it was a minimal amount of code to be able to create something as complex as this. This is one of our largest jobs, called our nightly job, and it's a great name. But there's a lot of, you'll see on the left are all of our external sensors that were other jobs on other Airflow or imports or things like that we were waiting on to be complete in order for our process to start. Each one of those pieces would have, there would be data quality checks involved in that, where after the table was completely loaded, it would do duplicate checks or threshold checks or things of that nature, so that you were ensured that your data was up to your standards at the end of the process. And then at the very end, it would set its status as complete for each individual table back in our analytics Postgres database and allow other jobs to be kicked off from that. So one of the other ones was, how do we deploy code from on-prem at Pandora to Composer in the cloud? So the ways that we came up with to deploy, one of them would be an on-prem Jenkins build that uses a plugin that Google has for Jenkins to be able to push code to a Composer DAG bucket. All of your code in Composer is synced to a bucket. So whenever you create a Composer instance, there is a Composer bucket that is assigned to that instance. Inside of there is a DAGs folder and also a plugins folder. These are the two places that you need to deploy your code in order to run them in Composer. You can also just drag and drop manually into the Composer bucket using Google's console UI. That is a very simple way, but it's also a manual way. So the other one would be more of an automated build. The second one would be more of a manual process. But something we came up with at Pandora, because a lot of our analysts are not really used to command line performance, and so we came up with a view that would allow them to use a web page to sync a project from Bitbucket. This view looks like this. And this view, when you pulled it up, would go out to our internal Bitbucket repo, and it will pull all of the internal to Pandora, publicly available Bitbucket repositories. You could select which one you wanted. You could select the branch you wanted, and then individually you could select the commit that you wanted. And then when you push submit, it would sync that code to the DAGs folder on the server that it was running on Pandora. So we had to take this and move it to Composer to be able to do the same kind of thing. So on-prem, the view would build the git command and then sync directly to the file system because it would run the git command on as an external process in Python. On Composer, the web server is not running on the Kubernetes Composer cluster. So the web server doesn't have access to the file system where your DAGs are located or the data directory that you're allowed to do work in on Composer is located. So we had to think of it in a little bit different way, and we had to create a DAG to take care of any web server action and then send the DAG arguments from the web server itself. That is because of this Composer architecture right here. You'll see that the workers, the Redis, the Airflow scheduler, and the Cloud SQL proxy are all running on the Kubernetes engine, but the Airflow web server is running on the tenant project. Right? So it did not have access to the file system on the Kubernetes cluster itself. The downsides to a DAG sync are the Composer bucket is synced down to the container file system, but not back up. So you could not just sync the code to the actual local file system where the DAGs are located, because it would be overwritten the next time that Google synced your code from the bucket down to the file system itself. Another one is that Bitbucket projects must be made public within the organization in order to view them to pull a list of them. Pulls, because of the network from on-prem Bitbucket, are a little slow. This is to be expected because you're pulling them up to Google Composer. You have to sync the project code to home Airflow GCS data before doing an rsync up to the Composer bucket. The home Airflow GCS data was just a temporary location in order to sync the code there, so we did not have to overwrite everything in the bucket every time that we wanted to do a pull from Bitbucket. And that is it for me, and I will hand you over right now, sir.
Hi, everybody. I'm Wilson Lian. I'm a software engineer on the Cloud Composer team, and today I have the privilege of telling you all about some new features that we've rolled out recently in Cloud Composer. So something that we've heard a lot from our customers is how can I monitor my environments to make sure that they're up and running and healthy and making progress on DAGs, as well as determine whether or not I've provisioned enough resources for my environment to make progress, or to handle the workload that I'm throwing at it. And so to answer that question, the Composer data plane is now exporting metrics into Stackdriver. As you can see here, we're exporting information about the quantity and latency of both DAG runs and task instances. So you can see if anything has gotten stuck. We're also exporting information about the health of the Celery queue, including the number of Celery workers that are up and the length of the queue. Now let's flip over to the demo screen, and I'll show you how you can use these metrics. Okay, so you can see here, I built this dashboard earlier. Basically, we're showing on the left column the number of DAG runs and task runs over time. And on the right column, we have the latency of DAG runs and task runs over time. So if we zoom in on 1 hour, we can see that we have 4 DAG runs per hour for a single particular DAG called sometimes slow. And we can see on the right-hand side that the latency of that DAG run varies over the course of an hour. In fact, once every hour, it takes much longer than the other DAG runs in that hour. And if we look down at the task, I happen to know that this DAG has 2 tasks. One of them is called consistent1. It's a bash operator, and it runs fairly consistently. And the other one is called sometimes slow, and it's a Python operator. And I cheated for this demo, and I made it so that sometimes slow checks the time, and once an hour makes itself 1 minute slower than every other time that it runs. So this is a bit of a contrived example, but you can see how if you had some external dependency that was introducing latency into your DAG runs, you would be able to see this in a Stackdriver monitoring console. And additionally, you could go in and create an alerting policy. And so let's do that right now. We'll create an alert so that whenever that task is slow, we get an email. So we'll filter that by the task name and say whenever sometimes slow takes longer than 60 seconds, for 1 minute, we will get an email or some other notification. This is just standard Stackdriver monitoring stuff, and then we can save that. And likewise, we could do a similar thing for the celery queue. Normally, a celery queue length of 0 is a good sign. That means that your workers are able to keep up with the offered load. So we could set up an alert on the celery queue, and whenever it exceeds some threshold, we can get an alert and realize that we need to do some reprovisioning. So now let's swap back to the slides, please. So the next feature that I'm going to talk about is one that you can use to help improve the security of your Cloud Composer environments. So whenever you create a Cloud Composer environment, as Dan pointed out, the Cloud Composer control plane is going to create a GKE cluster and Cloud SQL instance for you. And by default, the VMs for the GKE cluster and Cloud SQL instance will have public IPs, meaning that they are externally routable and you can be reached from anyone on the internet. Moreover, the communication to your Airflow database in the Cloud SQL instance will traverse the public internet. So what this means is your traffic potentially traverses the public internet, and if you have, say, a zero-day vulnerability in some daemon running on your system, it could be exploited by someone on the internet. However, with private IP clusters, we only assign internal, non-publicly routable IP addresses to all of your GKE VMs and the Cloud SQL instance VM. Optionally, you can enable a feature which will put the Kubernetes master for your GKE cluster behind a private-only IP as well. So let's swap back to the demo screen, and I'll show you how you can create this. You can do this using the beta channel of the gcloud tool, but you can also do this in the GCP console by enabling beta features up in the top right corner. Let's just look at what a private IP cluster looks like. Okay, so I pre-created this private IP cluster earlier. You can see that a private environment is set to true, and I have master external access set to false. So the Kubernetes master should only have an internal IP. So if we drill down into the GKE cluster that's associated with this, we can see that the master endpoint has an IP address 172.16.0.2, which is an internal IP address. And if we look at the node pool to check out the GCE VMs that were allocated for this, we can see that they have no external IPs. The last feature that I like to touch on is one that we've been working on for a long time. And basically, let's say you're really excited when you get out of here to go and try out this stack driver monitoring feature or some of the new features that you've seen us announce in recent releases. In the past, we would have asked you to create a new environment and then move all your DAGs over and then move all your Airflow metadata over to the new environment and then take down the old environment. Now, with just the push of a button, you can upgrade your environments in place and preserve the VMs, the Cloud SQL instance, and all your Airflow metadata on the same environment while still running the latest version of Composer or even an upgraded version of Airflow. I can try to demo this, but I will see if we're able to try that. Let's go back to the demo screen. So I have this environment here that's ready to be upgraded. I've enabled beta features, and we can see that it's running Composer 1.3.0 and Airflow 1.9.0. So if we just hit the upgrade image version button, we can select a new image version. 1.6.1 is our most recent version, and let's upgrade to the latest version of Airflow. Hit submit, and then the upgrades is in flight. It'll complete in a few minutes, and then you'll be at the latest version. That's all I have. For more information on Cloud Composer or Airflow, you can check out these links.